Okay, here's a problem that we did in lab and that you saw on a recent quiz. So try to answer the question as far as you can, including diagrams and derivation, and then come back and check what you did against what I'm going to do after you come back. Okay, you're back. First thing we do is we take the stick. Let me get the stick. And we find the center of the mass. So we place it over the back bracket, and at the point that the stick balances, that's what we call the center of mass of the stick, and we notice the position, and it's going to be close to 50 centimeters, but generally not 50 centimeters. So let's say in this case it's 50.5 centimeters. So that's the position of the center mass of the stick. That's step number 1. Then step number 2, I'm going to erase this. Whoops. And redraw the diagram. So now we take the stick, I'll make it a little bit bigger this time. We take the bracket and put it off center. And then we take the mass with the loop of string, and then we hang the mass. Whoops, the mass is hitting the floor. And so what do we need to notice? We need to put the center of mass mark there. And so it's the stick that's, I'm going to mix the diagram and the free body diagram. You're not supposed to do that, but there's the force of gravity on the stick acting at the center of mass, tending to tip the stick to this side. And then there's a force acting through the string on the stick. So this is the mass of the stick times g. That's the weight of the stick, tipping it this way. And then the mass is pulling on it this way, so that's the mass of the mass times g. That's the weight of the mass pulling the stick in a clockwise direction. And of course, for completion, we'll put the force of the stand, the bracket stand, up on the stick, so that the sum of the forces is 0, and in this case the sum of the torques is 0. And so we need to know, in order to calculate the sum of the torques, we need to know the distance from our axis here to where the force of gravity is acting, and we call that our stick, or our center of mass. Let me call it our center of mass. Yeah, RCM is a better designation. And then we have the distance from where the stick tends to rotate to the point of application of the hanging mass, and I'm going to call that Rm. And so you see we have only 2 torques, because this force here, this pivot force, doesn't exert a torque. It's acting through the axis. So we have the m stick g force over here acting down. We have the mg force of the mass acting here, so 2 equal and opposite torques. And that's how we're going to solve the problem. So let me squeeze this in. I'm going to go, so this is my combined diagram, free body diagram. And I'm going to use sum of the torques equals 0. And you see we have the counterclockwise torque, which is, remember, going over here, torque is equal to a distance, a force, sine theta. A little bit hard to read, so a distance, a force, and an angle in our torque. So we go to the counterclockwise torque. It's going to be RCM MSG times the sine of 90 degrees. I'm not going to write that in. That's just 1. Then the torque in the negative or clockwise direction is the Rm, the mg, and another sine of 90 degrees, and that's all equal to 0. And if we do the algebra, we can divide by g. We're going to end up with a simple expression that the mass of the stick is equal to the mass of the mass. I'm rearranging the symbols a little bit, but you can do the algebra, times Rm divided by Rcm. A little bit hard to read, but you get the idea.